If you drop an apple, it falls. If a ball is hidden under a cup, it continues to exist whether you are looking at it or not. For centuries, our understanding of the universe relied on two basic rules. The first is local realism, the idea that objects exist in a definite place with specific properties, completely independent of observation. The second is determinism, the logical rule that every single event has a clear prior cause. Quantum mechanics has contradicted those rules for nearly 100 years. The mathematics described a fuzzy, indefinite world at the atomic scale, but because the equations perfectly predicted the behavior of practical tools like semiconductors and lasers, the disturbing philosophical implications were largely ignored. The scientific community treated the strangeness of the quantum world as an intellectual exercise for philosophers. But between 2023 and 2024, that theoretical grace period ended. Google and IBM have successfully built industrial-scale systems that process information by leveraging the most counterintuitive principles in physics. These machines function by manipulating phenomena like superposition and entanglement at a scale and precision previously thought impossible for any engineering project. The reliable operation of these machines presents a direct challenge to our understanding of the world. They function by exploiting rules that should, by all accounts of common sense, be impossible, suggesting that our everyday experience of a solid, predictable world only tells part of the story. To understand why this is happening, we have to look at entanglement. Two particles can become linked so deeply that measuring one instantly affects the other, regardless of the distance separating them. Albert Einstein resisted this idea. He called it spooky action at a distance and insisted there had to be hidden variables, secret local mechanics we just couldn't see it, keeping the universe logical. Last year, the quantum processors at Google and IBM finally put Einstein's hidden variables to an empirical test. Researchers created entangled states of up to 53 qubits, running massive, continuous experiments known as Bell tests to see if any classical explanation could account for the results. This diagram visualizes a Bell test in action. By measuring the entangled particles across millions of trials, researchers look for statistical correlations. If Einstein's hidden variables existed, those correlations would hit a strict mathematical limit. But the qubits consistently cross that theoretical limit, proving no local hidden variables determine the outcome. The data shows these particles remain indefinite right up until they contact the measurement barrier. They have no fixed properties until observed. These experiments confirm that Einstein's objections were incorrect. Reality genuinely does not exist in a definite state until the moment of observation. If properties are only created at the moment of measurement, how is the outcome decided? When you flip a coin, the result is determined by physical factors: thumb force, air resistance, and gravity. Classical randomness is just a lack of information about the starting conditions. Quantum computers operate on a different principle. They use confirmed Bell violations to generate certified random numbers. These data points are guaranteed by the laws of physics to have no underlying cause or deterministic origin. This certification proves that the outcome of a qubit measurement is truly indeterminate before it happens. No amount of information about the state of the universe could possibly predict the result. The universe improvises. We must accept the fact that some events occur entirely without a prior cause, reason, or physical explanation. If questioning the fundamental nature of your reality is why you're here, make sure to hit subscribe and like this video. It helps us to code the universe, one terrifying discovery at a time. The scale of this phenomenon has moved beyond the microscopic. A quantum computer holding a 100-qubit superposition exists in over 1 non-million states simultaneously. This represents more parallel configurations than atoms in the universe. Executing quantum algorithms require these parallel states to function as physical resources. They act as the essential fuel used to teleport data and perform calculations that exceed the capacity of any classical machine. Quantum mechanics dictates that unknown states can be moved or destroyed, but never duplicated. This physical constraint treats information as a tangible substance, a core building block of the universe, on par with matter and energy. If superposition is a physical reality at the scale of a computer chip, why don't we experience the macroscopic world in the same way? This is the measurement problem. We need to know why we don't observe humans or cats existing in multiple places at once. The answer lies in decoherence, which acts as the universe's ultimate disguise. As this diagram shows, when a quantum system interacts with its environment, it leaks that information into the surrounding world. The superposition isn't destroyed, it is simply dispersed into the background noise. Recent error correction experiments have proven that this process is theoretically reversible. This implies that the supposed collapse into a single concrete reality may not be a fundamental physical event, but a practical result of information spreading too far for us to track. This suggests a jarring conclusion. Definiteness is an emergent property. We inhabit a fuzzy, indeterminate universe where the sharp clarity we perceive is a trick of our limited biological perspective. A functioning quantum computer acts as a physical probe into the underlying structure of reality, a structure that remains deeply unsettling to our most basic intuitions. We've barely scratched the surface of the quantum abyss. If this video changed how you see the world, share it with someone who needs their reality checked. Subscribe to The Explainer, and we'll see you